This is the second video in a series where we explain what a reversible isothermal gas expansion is. Okay, so let me take you to the end of the first video, in which what we were trying to do is have this gas expand against an external pressure that was constant, and we were controlling what that external pressure was by changing the mass resting on this tray that is compressing that gas in. Obviously, if you start to reduce the mass, then what happens is that the external pressure becomes lower, and then that gas can expand. Okay, so what we've done is actually seen that there is a sensitivity to the amount of work that can be done depending on how you reduce the external pressure. Okay, we've said that if you remove it directly, then no work is done because you're not pushing against anything. But then if you're doing it in two steps, first removing the mass from the initial mass to 1/4 of the mass, and then plugging the mass entirely, then you get this much work. But if you were to do the same thing now in 3 steps, okay, in which first you remove the mass to make it half of the initial value, and then you take that half mass left over and reduce that by 1/4 of the initial mass, and those 3 steps you actually have that you have more work. Okay, so the question is, well, this is useful. I see that if I do more steps, then I get more work. The question is there an upper limit for how much work I can get out of that? Okay, so well, yes there is, and that's what we're going to see in this video. That's what we're going to be calling a reversible isothermal expansion. The idea is that the more steps that you do this, that you involve in the process, the more work you will get out of that. So there is a limit to how many steps you could do, which would be an infinite number of steps. Right, so the idea is that this will be an idealized process. You will never be able to do this in practice because it would take an infinite amount of time to do infinite steps. But this is how you would do this if you have infinite time. What you would do is you simply take an infinitesimal amount of mass and then remove it. Let the system equilibrate, reach a mechanical equilibrium, and then remove another infinitesimal amount of mass. Let the system equilibrate, remove another little bit of piece, little mass. Again, this is going to be an infinite number of steps, but you can clearly see how the mass is changing a little bit at a time. So what that means is that the external pressure is decreasing, and that means that the gas can expand a little bit at a time. Again, if you would have infinite time, then this would give you maximum work, which is what we're really interested in. The question is, well, in practice that is going to be impossible to do, but can we actually predict how much work you would do out of that expansion? Okay, and the answer is yes. And that is what we call a reversible isothermal gas expansion. Here's how it works. Let's think about just one of those tiny little steps in which we simply remove a little bit of the mass, an infinitesimal amount of mass, and let the system expand. What we would say there is that the work in that particular step would be equal to the minus external pressure times the change in volume. But because this change in volume is infinitesimal, then there is not going to be a delta V, there is going to be simply a differential of V. Okay, so you can clearly see that this is going to involve calculus. Right? That will be the work in one of the infinite number of steps. To get the total work, which is what we're trying to do here, notice that what we need to do is just sum all of these steps, and that can be done via integration. Right? That would be the external pressure multiplied by the change in volume in that step, and then we have to do this from the initial volume to the final volume. Okay, so that's the integral that we have to solve to calculate work in this idealized process that gives us maximum work. All right, great. So the question is, well, how do we calculate these initial volumes, final volumes? Well, the initial volume I already know, that is V1. Okay, and the final volume, we're simply going to stop at this point, okay, which is the point that gave work in these 2 expansions where we actually had any work done. Okay, remember that at this point, if you decrease the pressure by 1/4 or by a factor of 4, then the volume increases by a factor of 4. So what that means is that my final volume is going to be 4V1. And again, notice that this is exactly the same final volume that you had up to this point in this expansion and then that expansion. Okay, great. So then let's try to see how do we integrate this. Well, the idea here is that what happens to the external pressure. And here's something that is very important. Notice that the external pressure, as you go going through this expansion, is actually not constant. Okay, the external pressure is changing because you're changing the mass a little bit at a time, right? So this is not a constant. You actually have to integrate. But the question is, well, what is that value of the external pressure? Okay, so here's a key point that is quite important here. Okay, the key point is that when you remove an infinitesimal amount of mass, you're letting the system equilibrate so that the pressure of the gas is identical to the external pressure at any point during the expansion. Okay, so again, you remove a little bit of the mass, the system will expand, but at that point, the pressure of the gas will be identical to the external pressure. You reach mechanical equilibrium, and the expansion can't go any further. You take a little bit of the mass, and then the gas can push that piston a little bit, but the pressure is equilibrated. You get mechanical equilibrium. The expansion stops. Remove another little bit of mass, and so forth. Again, importantly, what happens there is that at every point, the pressure of the gas equalizes the external pressure, and that is something that we're going to be able to use right here. Again, if we do that with an infinite number of steps, which will always be the case, is that the external pressure is going to be equal to the internal pressure of the gas at any point. Okay? And again, that happens for your reversible process that takes an infinite amount of time. And this is nice because now we can actually use the equations of the ideal gas equation of state, P of the gas times volume of the gas is equal to A nRT, to figure out then what this pressure of the gas is. Notice that what you have right here is that the pressure of the gas is simply going to be equal to nRT over the volume. So you can come here and say, well, that is going to be the integral from the initial volume V1 to the final volume for V1, and that is going to be minus nRT over V differential of V. And that seems a much simpler integral to solve than what we had before. Okay? Right. Notice that N is the number of moles of the gas, but that doesn't change, so that is a constant. R is a constant as well, that is the ideal gas constant. And the temperature is constant because this is an isothermal expansion. So these three values are actually constant, which means that I can take them out of the integral. So that is going to be equal to minus nRT integral from V1 to 4V1 of differential of V over the volume. And now that is an integration that you can do fairly easy. Notice that that is going to be the natural log of the volume. So your final answer is going to be minus nRT natural log of the final volume over the initial volume. For this particular case, we have that the final volume is 4V1, so then we can replace that by 4V1. And the initial volume is V1, so that is just V1. Okay, what that means is that these two things can cancel, and then what you have here is that that answer will be minus nRT natural log of 4. Okay, what about this nRT? Notice that the work in these particular steps was expressed as P1 and V1. Okay, so notice that we can actually make the relationship here. At the start of the expansion, we have that P1 and V1 are equal to nRT. Okay, so this nRT that we have right here is really P1, V1. Okay, so to finish this, the answer is going to be minus P1, V1, natural log of 4, which is equal to minus 1.4 P1, V1. Okay, that is our final answer for this idealized process. Okay, there is actually the upper limit of work that you could get in this gas expansion that we have set up right here. Notice how nice this is. Okay, if you make this expansion in just one step, you don't get any work done. You do 2 steps, as written here, you get minus 3/4 P1, V1 of work. If you get it in 3 steps, then you get minus P1, V1. If you do it in infinite steps, then the upper limit will be minus 1.4 P1, V1. So you certainly extract more work here than you do there, Okay, but there's just simply no way that you can extract more work than that. Okay, so as you can see, the reversible process in which you have equilibrium situations as you move along, okay, is an idealized process, but it's a very useful one because it gives you the upper limit for the amount of work that you can extract. There's no possible way to extract more work than this, so this is always going to be a benchmark against we will calibrate how good our expansion is, right? Whether we're getting close to the upper limit, or yes or not. Okay, so again, in this video, in the last couple of videos, we have explained what a reversible isothermal gas expansion is. The idea here is that a reversible process is one that occurs through equilibrium steps. Okay, it's an idealized process. It can never be done in reality. Okay, but the usefulness of that idealized process is that it provides the maximum amount of work.